This video will cover section 5.2, integration with the natural log function. So in the last video we covered the derivative of the natural log, so now we're obviously going to be doing integration. So recall that the derivative of natural log of u is the u prime over u. So that means if I take the integral of something that looks like u prime over u, then I can rewrite that as 1 over u, and what u prime really is a derivative of u, and so then that would equal the natural log of u plus c. However, you have to make sure and be careful with the absolute value piece, because when I go backwards into taking an integral that ends up being a natural log, you have to make sure that whatever that u is inside absolute value. When I take a derivative of a natural log with absolute value, the derivative, you can knock that absolute value out. It doesn't matter. However, when you integrate something that has natural log as an answer, you have to have absolute value around that u. Because whatever that function was, u, it might not have had the same domain as natural log, where x only had to be greater than 0. So you have to make sure that whatever is inside there is greater than 0. Alright, so we're going to evaluate each indefinite integral involving something of the form u prime over u. So we're going to go back naturally to u substitution. So looking at a, we look at what's in the denominator typically is going to be our u. So let's see how this works out. So if u is 6x plus 1, then du is just simply 6dx. And as I've shown you before, if I want just dx, then that would be 1/6 of du. So let's put everything in terms of u. So we get 1 over u, and then dx is 1/6 du, which I'm going to put 1/6 out front. Now you can simply take the integral, and the integral of 1 over u du is the natural log of the absolute value of u plus c, but then we need to put things back in terms of u, so that would be the 1/6 natural log of 6x plus 1 plus c. Alright, so pretty straightforward there. Typically I can go, most of you, once you get practice, from this step to this step, basically doing all that u substitution kind of in your head once you get practice with it. But for now, make sure you are showing the steps so that you don't miss anything. Because what will end up happening is you get so used to doing that, is that you end up forgetting this 1/6 here. Alright, so don't forget that. Alright, so let's look at b. So for b, our u would be the x squared plus 2x. du would be 2x plus 2, and look at there, we've got it in our numerator, so that's very nice. And that's the dx there. So we don't have to manipulate anything. We've already been given it. And I'll go ahead and tell you that hardly ever happens on an actual test. So this has been really nice. So then we have 1 over u du, and then we get, that's the natural log of the absolute value of u, which is x squared plus 2x. And don't forget your c. Pretty easy. Let's look at one that's a little bit more challenging, a little bit more interesting. So looking at c, if you try to do the same thing that we did with part A and B, and you just simply say, okay, well, let's use what Ms. Freeman's showing us, and let's just make u be sine squared. Think about this for a second. If you made u be sine squared, then du would be 2 times sine times cosine. And I've got nothing like that. I've got tangent, which is sine over cosine, but really doesn't help me with anything if that was my u. So what you're looking for, let's get back to the beginning. What you're looking for is some version of u prime over u. So you're looking for whatever's in the numerator to be a derivative or a form of the derivative of whatever is in the denominator. And when you've got tangent over sine squared, that is not the case. So you want to rewrite tangent and sine squared in a format that you've got u prime over u. And that does take a little bit of guess and check. Because you've got so many different ways you can take this. But the way that I would take this one is if you simply switched these. So if you took the reciprocal, basically. of both of these, tangent being 1 over cotangent and sine squared being 1 over cosecant, and then simplify that, you'd really get cosecant squared of x over cotangent of x dx. And now if you look at this, if the u is cotangent, the derivative of cotangent is cosecant squared, or actually negative cosecant squared. So this is really going to be very imperative that you start to memorize your trig identities and also your trig derivatives and integrals so that you can see that relationship. Because if you had forgotten that derivative of cotangent is negative cosecant squared, then you would have never been able to do this problem. So u would be cotangent, and du would be negative cosecant, you can spell that, squared dx. So the only thing you have to change here is we need to make this a negative 1 over u du. So the answer would be a negative, natural log of cotangent x plus c. Which I want to point out here, using our log rules, because again, I want to talk about simplifying expressions for the multiple choice section especially. If you have a negative natural log of cotangent of x, what that also is the natural log of cotangent inverse cotangent. Nope, sorry, that is incorrect. Hold on. It's cotangent to the negative 1, but it really means the reciprocal, because when you have the log rules, it means the reciprocal of that. So the reciprocal of that would be 1 over cotangent. It's not arc cotangent. So it's the reciprocal, not necessarily to the negative 1 power. So then 1 over cotangent is then tangent. So I just want to make sure that you see that this is equal to this and vice versa, because you may see that on a multiple choice part test. Okay, and just one other example here. So let's think about it before we write it down. If u was x squared plus 3, du is 2x, which is a form of our numerator, so we're good with that. So let's do that problem. Okay, so then we have a 1/2 that we can pull out, and then a 1 over u du. So this would be 1/2 times the natural log of x squared plus 3 plus c. Now there's a couple of things here. The reason I wanted to do this problem was to talk about how to simplify again. So first of all, I know I said to always include absolute value when you get a natural log out of an integral. But what if that u is always positive? In the case with x squared plus 3, no matter what you put in for x squared plus 3 will always be positive. So actually, to be completely right, and I know you wouldn't be wrong putting the absolute value, but actually to be completely right, there you need to put parentheses. And there are some people who would take off if you left it as absolute value. I would personally not take off, but on an AP exam, since it's technically incorrect if you leave the absolute value there, I have heard that there have been times where they take off, so just keep that in mind. And another thing you could do and might see is that 1/2 could become an exponent, leaving that to be the natural log of the square root of x squared plus 3. And then you could lose the parentheses and absolute value altogether. Now, you couldn't lose the absolute value, though, if that wasn't always possible. Okay? So that would be kind of our final simplified answer. Okay, so using natural log from an integral only works if you have the pattern u come over u if the degree of the numerator is 1 less than that of the denominator. Because if you use the denominator and we take the derivative, then we get 1 less degree. However, what if you have the degree the same, or the degree of the numerator being higher? So what happens here now is if you have the degree of the numerator is greater than or equal to the degree of the denominator, then what you want to do is to divide. Okay, everyone's favorite, long division. Now I tend to use log division, polynomial division, You can also use synthetic division. However, that's one that I don't ever use synthetic division, so I don't really remember it. So I use polynomial division. So that's what I'll use for this class, but if you would like to use synthetic, you remember and you like it, then by all means, that's fine. All right, so looking at part A, we have a degree in the numerator is 2, and the degree in the denominator is 2. So since they're the same, we are going to do long division first. So that is x plus 1 divides into x squared minus 3x plus 1. Okay, so let's recall how to do this. X squared goes to x squared once, so then we multiply x squared times 1 is x squared. Sorry, and then 1 times 1 is plus 1, so that leaves 0x and then plus 1. So then just like you learned in elementary school, we're going to subtract, put parentheses around that whole thing. So x squared minus x squared, that'll just be 0. Negative 3x minus 0x will be negative 3x, and 1 minus 1 will be 0. So this is our remainder. So the way this is going to be equivalent will be, we get an answer of 1, so that's just there, plus our remainder, negative 3x, over what I divided by x squared plus 1. Okay, so just hopefully you remember how to do that. If you need help, you can come see me. But this whole expression here is equivalent to that whole expression there. So now what we can do is we can separate this actually into two integrals. So this could be the integral of 1 dx. And then what I'm going to do is I'm actually going to pull out this negative 3 and say that's minus 3 times the integral of x over x squared plus 1. I just like to do that because I like to keep my integrand as clean as possible. So I'm going to pull out that negative 3. Okay, so now the integral of 1, we can just do that by ourselves. No use substitution or anything fancy is x. Then minus 3. And so what we're going to have to do with this integral is actually go back and do u substitution. So I think we did one almost just like this, but so u is x squared plus 1, du is 2x dx. So x dx is equal to 1/2 du. And so that 1/2 I'm going to pull out with the 3 there. And then that's going to be times the integral of 1 over u du. So then my final answer will be x minus 3 halves times the natural log of the absolute value of u. U is x squared plus 1, so we don't need absolute value, plus c. Okay? So just to recap there again, if you have an integral with a polynomial or a rational function, polynomial divided by a polynomial, and the degree in the numerator is greater than or equal to the degree in the denominator, do long division. Okay, another long division example. What I'm going to do is I want you to actually pause the video on this one, work it out yourself, and then restart and see if you get the same thing as me. Okay, I'm going to stop there. I'm going to show you what I did with the long division and what the integrands became for me before I take the integral. So just look at that, make sure everything makes sense, and now I'm going to integrate. Okay, so here's the final answer. So notice that I split it up into two integrals. The integral of 1 over x, I did show the u substitution here. I typically don't do that. Just make sure that it doesn't become a problem if your du is anything but dx, and that can become a problem. Okay, so let's look now at part C and talk about what's going to be our u and our du here. So this one actually combines a couple of things. So we have the integral with the natural log here. And we actually haven't even talked about the integral of natural log. So knowing that we don't know the integral of natural log, our u is going to have to be, include that natural log. All right, so it's not going to be the very inner function of x squared. It's going to actually be the natural log of x squared. So then when I take du there, what we learned from last time, that's u prime over u. So that would be 2x over x squared, which then when I simplify, it's just simply 2 over x dx. So what you can see now is I've got this 1 over x, and so all you have to do is say that, what is it, 1/2 du is equal to 1 over x dx. Okay, so you can see how we deal with that. So typically, if, not typically, always, if natural log is inside an integrand, then that's going to be part of your u. So then we have 1/2 times the integral of 1 over u du. So our answer is 1/2 the natural log of, yes, the absolute value of natural log of x squared. Okay. All right, for the next one. Now what we can see is you're not going to do long division with d because the degree in the denominator, or the numerator, is less than the degree in the denominator. So this would not be use of, or not use, this would not be long division. This would simply just be where u is the denominator. But notice here that what's in the numerator is x plus 1. So we can just manipulate here 2 times x plus 1. So then we have, again, x plus 1 dx is equal to half du. All right, so then that would be 1/2 integral of 1 over u du, which would be 1/2 natural log of absolute value of x squared plus 2x. Okay. Okay, so I know this is not the most exciting of videos, it's just working a lot of problems, but really when we get to this kind of section, it really is just getting used to different types of problems. So what I'm doing in these notes is just going through and trying to hit every different type of problem that you're going to see. So this is another one. We have x over the square root of 9 minus x squared. If I make the u be the whole denominator, the square root of 9 minus x squared, then you get a really gross du. So I'm going to leave u as 9 minus x squared, because then when I take the derivative of that, you get, I can write, negative 2x dx. So you've got your x in the numerator, so then all you have to do is divide by negative 2. So that will be a negative 1/2 integral of 1 over the square root of u. Now at this point, a lot of people want to say, oh, that's just natural log of the square root of u. Incorrect. All right, so make sure you watch out for that. A lot of people, when they start doing the natural log, they say anything, if you have 1 over something, will be natural log. But that is wrong. 1 over the square root of u is actually u to the negative 1/2, which is then going to just be powerful. The reason why we have to use natural log is because when we have 1 over u, and the degree of u is 1, okay? So the degree of u in this problem is 1/2. So we only use natural log if the degree of whatever is in the denominator is 1 when I integrate, okay? So if you go in terms of u, and the degree is not 1, then you cannot say that that's equal to natural log. All right, so now I'm just going to use the power rule here. So this is going to be negative 1/2 times u to the positive 1/2, coefficient of 2 plus c. So then that's going to be negative square root of 9 minus x squared. All right, yet another problem. So what I want you to do on this one, I'm going to pause. I'm going to let you try it on your own. I'll pause kind of in between and see how you're doing. Okay, this is quite a strange problem. I probably shouldn't let you try this on your own, actually. But hopefully you try. So if u equals, it has to equal the whole denominator, because otherwise it's really not going to help us out at all if we make u be 3x or something like that. So if u is 1 plus the square root of 3x, I take a derivative, and yes, it does look nasty. And I know I try to steer away from things that look nasty, but there are some cases where you just have to do nasty stuff. All right, so du is 1/2 3x to the negative 1/2 times 3, which simplifies down to 3 over 2 square root of 3x dx. All right, obviously, nothing like that is sitting over here under our integral. So what I did instead is I went ahead and solved for dx. So I multiplied by the reciprocal. And now I have something that still has an x in it. So what you can to see here is if I try to solve for x, my first step is subtracting 1. So I get the square root of 3x equals u minus 1. But look at what I have to do. I don't have to continue solving for x because the square root of 3x is sitting right here. So then you get 2 times u minus 1 all divided by 3 du, and now you have dx in terms of u only. It's really kind of a crazy one, but sometimes you do have to manipulate that much. Good news is I don't see very many of these very often, because to try to get that on your own is pretty difficult. So let's go ahead and see what we can see over here on the left. So this is going to be the integral of 1 over u, and then dx is, I'm going to go ahead and distribute, oh no, I don't have to distribute, 2 times u minus 1 over 3 u. So the reason I didn't distribute is I can pull the 2/3 out, and then you get u minus 1 over u, which then I'm going to simplify to 1 minus 1 over u. So I took that really nasty thing and actually made something quite easy. So now I have 2/3 times the integral of 1 is u minus the natural log of the absolute value of u, and then replaced in terms of u, or in terms of x. So that's 2/3 times 1 plus square root of 3x minus the natural log of 1 plus square root of 3x. And that should be parentheses there. Okay, so let's do a definite integral this time. That means we have limits of integration. So for this one, we have, you see the degree in the numerator is the same as the degree in the denominator. So polynomial division. So x plus 1 goes into x minus 1. And I know that looks strange, but that's how we do it. So x goes in x one time. So we get x minus 1, subtract, and we get, oh, hold on, what did I do? Okay, sorry, that should be plus 1 there, and then you have negative 1 minus 1, which is negative 2 as our remainder. So this becomes the integral of 1 plus negative 2 over x plus 1. Okay, so then from 0 to 1. So now I can separate that into 0 to 1 of 1 dx plus, or actually minus 2 integral from 0 to 1 of 1 over x plus 1 dx. Okay? Now, to actually show you everything with the u substitution here, I want us to put everything in terms of u. However, the integral from 0 to 1 of 1, I'm just going to go ahead and say that that's equal to x from 0 to 1. And then minus 2, what I'm going to do now is let's review how to do u substitution with definite integration. So u would be x plus 1, du would be dx. So this would now become my integral, oh, I should have put that in from, if x is 0, then u is 0 plus 1, which is 1. If x is 1, u is 2. So then that's 1 over u du. So then if I evaluate x, that's going to be 1 minus 0, which is 1, minus 2 times the integral of 1 over u is natural log of u, from 1 to 2. And so now I don't have to go back to in terms of x. I can simply say that's 1 minus 2 natural log of 2 minus natural log of 1. And I know that the natural log of 1 is 0. So this is actually 1 minus the natural log of 2 squared, which is 4. Okay? All right, now what I'm actually going to do is I'm going to skip the integral of tangent. We talked about that in the last example when we took the integral. So hopefully you remember the example that we did with tangent. And so the integral of tangent is the natural log of absolute value of secant x plus c. And these are ones that I do want you to be familiar with. Secant, we also did that one. And then if you got these two, tangent and secant, you can pretty much get the other one. So cotangent is going to be the natural log of the absolute value of sine. Another way that you could think of it is it's actually the negative natural log of cosine, but the negative natural log of cosine is the same as natural log of sine. And then cosecant will be the negative natural log of cosecant x plus cotangent x. Okay, so just keep those, make sure you run over those, especially tangent and secant. Okay, we are almost done. I know this video is really, really long, but we have one more example to look at. And so this is another second fundamental theorem of calculus. So if we have capital F and we want to find F prime, then F prime, remember we don't have to do any derivative or any integral of 1 over t. That's simply going to be 1 over the upper limit times the derivative of the upper limit minus 1 over the lower limit times the derivative of the upper limit, of the lower limit. Then that will simplify to 1 over x minus 1 over x, which is lovely. It turns out to be nothing. Alright, so I know that these were really long videos, but hopefully you were able to understand them. Please go back over the more difficult problems if you need to, and we'll look